The grand challenge selected for Team 9's Engineering 1300 semester project is Improving Modern Infrastructure. We decided to tackle this grand challenge by addressing the state of building safety and congruity in the face of a natural disaster: earthquakes. The fear of earthquakes can be attributed to one main factor: a lack of knowledge. Our goal is to properly demonstrate how buildings and other structures react in the face of seismic activity. To do this, we've designed and developed a functional shake table. A stepper motor is powered by code produced in the Arduino IDE to swiftly rotate, which then moves belts attached to the base of the table. Together, these components cause the table to rock similarly to that of actual earthquake activity. Compared to other products already on the market, our product features a 3 by 1.5 foot scale, both wider and longer than current affordable options. This allows for multiple building models to be tested on the same platform, which provides a more realistic scenario where buildings are often right next to each other in urban cities and other populated areas. Using a shake table to give a visual demonstration of earthquakes help us better understand the real-world systems that are already in place that keep buildings upright during disaster. It also helps us theorize the potential for better, stronger bindings in a safe and controlled environment.
Our project incorporates both general and specific performance specifications by focusing on accuracy, safety, and educational value. At a general level, the shake table must reliably simulate earthquake motion and support repeated testing with our different building models. On a more specific level, we designed the table to use an Arduino-controlled stepper motor that produces consistent and measurable vibrations. Our structures must remain stable with the seismic forces that we use to test them, as well as the dampeners underneath must absorb energy the way real-world systems do. These specifications ensure that the project functions as both a demonstration tool and a learning experience. Our design stands out because it combines engineering accuracy with hands-on engagement. Unlike typical static displays, our shake table allows users to build their own Lego structures and immediately test how well they withstand multiple earthquakes. The 3D printed dampeners and side-by-side comparison buildings make the demonstration visibly clear and interactive. This adds value by making complex engineering concepts accessible as well as easy to understand. The design connects directly to the theme of improving modern infrastructure because it demonstrates real seismic resistance strategies used in modern buildings. To solve the problem our team selected, we analyzed how earthquakes impact buildings and what engineering methods are used to reduce structural damage. We studied shake table mechanisms and real seismic dampening systems, as well as building materials to determine what could be realistically replicated at a smaller scale. From there, we designed an affordable, portable shake table with an Arduino-powered motor, paired with model structures that highlight the strengths and weaknesses of different building designs. Through testing, we built a system that demonstrates how engineering directly affects a building's ability to survive an earthquake.
So we started using CAD, designing the prototype and the final design mainly using software like Onshape. And then I moved to working on the electronics behind the shake table like the Arduino and motor. We 3D printed the box for them that could hold the motor, pulleys, Arduino, and the motor controller. When we finished making the electronics for the build, we verified that they worked and then moved on to designing the frame for the shake table. We got particle board for the base and 2x4s for the rails on the side and then attached them together with wood screws. After that, we went on building the shake table, which used particle board that was CNC to save weight and then put it on the caster wheels that it will roll on. Then we attached the belt to the motor and the shake table and made some acrylic plates with laser cutters for aesthetics. Last, we made the model that would go on the shake table, and they were just wooden buildings, 3D printed springs, and a shock absorber. So we had some innovations while doing our build processes. First was when we moved the caster wheels from being attached to the shake table to being attached to the rails to reduce the moving mass on the shake table. Second, we got the particle board for the shake table and CNC square slots into it to reduce weight and put acrylic sheets on top of it where the buildings would rest. Last, we was to improve the dampening on the building, showcasing the technology. Originally, it was only had the springs for the base, which made it oscillate a lot. So we added an RC shock absorber that would help reduce the oscillation to make it smoother.
The final cost of the build was around $80 that was spent from purchasing the motors, the equipment, and tools for the project. One thing that I have learned from this project was sourcing the material was actually a key factor to our success on building the build. One thing I would do differently would be to take more time outside of class to learn the machines such as like laser cutting and CNC equipment to better streamline the process and for it to be more of a plug and play. The overall project has taught us how to use different engineering disciplines to create a single model, or using all those experiences to build something. And the process from designing from the digital and bringing it to the physical was actually a really fun experience, and to witness that was pretty cool. And one thing, our next step is to basically to refine the prototype and make it more accessible for others to use.